Okay, this is 1.7 inequalities, and we're going to be, in this video, I'm going to show you how to solve pretty much any kind of inequality. We talked about on the very first lesson how to do inequalities on the calculator, and you're going to want to keep that in mind as you check your work on these. But this particular video is just about how to solve these without a calculator. Alright, so let's start with a really basic one, and you've been doing problems like this since Algebra 1, so you should be able to do this really without me even going over it, but it does kind of set the tone for the rest of the lesson, so I'm going to explain it. This is a linear inequality. You're not just going to have one answer or one number as your answer, you're going to have an interval of numbers, and it should solve just like an equation. So you're going to subtract 3 and you're going to get negative 4x less than or equal to 15 minus 3, that's 12. And then when you divide by negative 4, remember dividing by a negative switches that inequality symbol, and then you have negative 3 over here. So this is okay for an answer, but I'm going to want your answers in interval notation. So if you think about our answer is all the numbers greater than or equal to negative 3, that is bracket negative 3 to infinity in an interval. Okay, there's another type of linear inequality, and this is sometimes called a triple inequality, sometimes it's called a compound inequality, and we're going to do a little bit of fraction review in this problem as well. So 1/6 less than negative 2x minus 13, that whole quantity over 12, less than or equal to 2/3. All right, now I see a lot of fractions here, and I want to clear that fraction. And I want to clear it in all three if I can. And that's why this is called a triple inequality or compound, because there's 3 parts. So I look at the least common denominator of all 3 parts, that's 12. So I'm going to multiply the whole thing through with 12. So 12 times 1/6, that's 2. The middle part, when you multiply by 12, it'll cancel out with the 12 in the denominator, and you're left with negative 2x minus 13. And then 12 times 2/3, 12 over 3 is 4, 4 times 2 is 8. And now you don't have a fraction to deal with. We still need to solve for x though, so we're going to add 13 to each side. And you should be able to do all of this without a calculator. Although if you need to show more steps, then that's fine. No shame in that. Okay. Dividing by negative 2. So this just gives us negative 15/2. Remember, switch the inequality when you divide by a negative. And notice that this kind of flipped around my triple or compound inequality. So I'm going to go ahead and rewrite it as, you know, a decreasing to increasing statement, meaning I'm going to write it where there's less than symbols here, and so that the lesser number is on the left, and as you go through the inequality, you're increasing the value of each term. That's going to make the next step of writing this in interval notation easier and accurate, because in an interval, you always go from least to greatest. So negative 21/2 is the least number here, and x is kind of stuck in between these two numbers. Now you need to pay attention to your inequality symbol. It's going to tell you whether to have parentheses or brackets, and we just use the same rules you've used all along. So notice the difference between the bracket and the parenthesis. Okay, now, oops, that kind of went to another page of notes. Here we go. All right. So let's say we have a higher order, and let's do a quadratic here, although this technique really will work for any polynomial. Although it's easiest with the quadratics. Okay, when you're trying to figure out the values of x that make this statement true, let's think about what this makes graphically. The left-hand side is going to make a parabola. The right-hand side really is just the x-axis. So you're looking for where is this graph below or on top of the x-axis. Now if you can find the roots, or the zeros, the solutions, then that's easy to do. And you know, algebraically, those are the solutions to the equation. So what you need to be thinking are, well, what are the solutions to the actual equation as well? And that's going to help us answer the solution to the inequality. Well, if you can factor this, that's definitely going to be the easiest way to find these. Otherwise, you're going to have to use quadratic formula, and -2 and -3 are the factors that multiply to get +6 and add to get -5. You may have to do grouping on this problem. We didn't on this one. And so I can see that my two answers to the equation are 2 and 3. All right, now if I put these on a number line, 2 and 3, first of all, let's think. Are 2 and 3 solutions to my original inequality? Since this is less than or equal to, they are. So I'm going to, let me back that up. I'm going to go ahead and put these as points. If this had been strictly less than, or in another problem strictly greater than, I would have put open circles here so that I know these numbers are boundaries. Now, in a typical polynomial, you're going to have an every other, meaning that your answers are going to be in every other section. So like in this problem, we could have shaded or true statements on the outside two pieces and not on the inside, or we could have it on the inside. And the more roots you have, it would follow this every other. Now, there are exceptions to that when you start having multiplicities and double roots and all that kind of stuff. So I'm going to give you a really easy way to check. If you're really good at thinking about this graphically, just think, is this parabola faced up or down? In this particular problem, it's up because the leading coefficient is positive. So if I want to know where is this less than or equal to 0, I'm looking for, let's just say this is our x-axis. I'm looking for actually the middle part. Okay, so I'm going to shade in from 2 to 3, and that is a way you can do it. Okay, if this had been negative out in front, that would kind of change up the problem, but we'll just say that's the only thing. Then we would have shading on the outside two pieces. Another way, which is really probably going to work for those of you that really just like more concrete ways to do things, is to test. So like to test a point over here, let's test 0. And what we're testing for is true or false. So if I plug 0 in for x, I would get 6 less than or equal to 0. That is false. So I would not shade here. Now, in a simple quadratic, that gives you enough information because I told you there's an every other shaded pattern. You definitely could plug in a number over here. I would plug in a number like 100. I wouldn't go for 4 or 5. You're going to have to do number crunching. Because if I plugged in 100, that's going to give me such a large value here. It won't matter what this is, and you're definitely going to get false nature. Plugging in 2.5 maybe would be your best choice here. That's kind of a bit of number crunching. I don't even think we need to do it because we already know it's false on the outside. So that, again, that tells us that we have shaded on the inside part. And all of those things confirm the same answer, which is all the numbers between 2 and 3, including 2 and 3. Okay? Let's try a rational now, because these are a little bit harder. And now all of these things you learned last year in different sections. You learned it as you went along. And so I'm kind of throwing a lot of things at you at once. And so if you have questions, write them down, or you can email them to me, or bring them up in class tomorrow. Okay, so here we have the rational expression 1 plus x divided by 1 minus x greater than or equal to 1. Now, there's a few different methods on how to do this. Like if you were to do an internet search, I can think of at least 4 different ways to solve this. And they're all great ways. I'm going to kind of keep this like what we just saw with polynomials, meaning we're going to find some test points, and then we're going to think about what the graph makes, and we're also going to think about true and false when we plug in values. Okay, so what we need to do is we need to compare this to 0 first of all, because that's a lot easier to do than to compare it to a number, and we need to think about what the graph then looks like. So I'm going to rewrite this as 1 plus x over 1 minus x, and then minus 1 greater than or equal to 0. Now I'm not really going to deal with the greater than or equal to much until we get to the test points. So if you were to write this as equals, that would actually be okay, because we're kind of solving the equation here. but we need to simplify this left-hand side. So we've already practiced this. It's all about getting a common denominator. And so our common denominator is going to be 1 minus x. And so if I write, I'm going to go ahead and write plus, just to make this a little bit simpler on myself. And if I'm going to multiply the denominator by 1 minus x, I have to do that to the numerator. And so then I have 1 plus x, and then plus minus, or negative 1 times 1, so that's minus 1, and then plus x. All over 1 minus x, greater than or equal to 0. The 1's cancel to 0, and then I get 2x over 1 minus x, greater than or equal to 0. All right, so let's think about what this graph on the left looks like. We don't have to actually graph it, but there's two main things I want you to think about. First, I want you to think about the solutions, okay, or the x-intercepts. This would be where this whole thing equals 0. So we're not looking at the denominator, we're just looking at the numerator. What value of x is a solution for an x-intercept? We get 0. Now I don't really care about the point, I just care about what the value of x is. Alright, so that's one thing. Alright, and since this is greater than or equal to, this actually is a solution. Alright, now the other thing you need to think about is a vertical asymptote. Alright, now this is really something we don't call a solution but a critical point, because it is where the graph changes, although this value, and in this case it's x equals 1. 1 is not part of my solution set. It can't be, ever, for a vertical asymptote, because if I plug 1 in for x, I get divided by 0. That causes the vertical asymptote. That's an undefined part of my graph, and my graph is going to change there, but it's going to affect my solution, but it's not part of my solution. So you're thinking, well, how do you piece this all together? Well, let's draw a number line, and let's go ahead and place, and in other problems you might have more numbers here, especially if your numerator or denominator were higher degrees. You could have multiple roots or x-intercepts, multiple vertical asymptotes. Okay, so let's go back to the solution. Since this is greater than or equal to, x equals 0 is a solution. So I'm going to darken that in. If this had just been greater than or just less than, I wouldn't put an open circle there. Now for your vertical asymptotes, you're always going to put an open circle because, again, that's an undefined part of the graph. All right, now's the fun part. All right, we need to think, what are the values of x, or what are values to the left, to the middle, and to the right? And on here, you may have an every other, but that was more of a polynomial rule. With rationals, you really need to test every section. So I'm going to test a number over here, and I'm going to test negative 100. Because negative 100 is going to be really easy to do that calculation in my head. I don't really care what the numbers turn out to be. I just care if it's true or false. Now you can either test the original problem or the new problem. I'm going to go ahead and go for this. All right, now if I plug in a negative 100, I get a negative on top, and I'm going to go ahead and kind of keep track of my work up here. I get a negative on top, and then I get a negative on the bottom. Now that's going to lead to a positive number. All right. I'm sorry, I get a positive. I know that didn't sound right. I get a positive on the bottom because of 1 minus negative 100. This would have worked for any negative number. I picked negative 100 because sometimes if you have to square it or something, it's easier to deal with a large number. Doesn't matter what number you pick, as long as it's less than 0. Now, negative divided by positive will always give you a negative. Since negative numbers are not greater than or equal to 0, I get false over here. So don't shade over here. It's not part of our solution set. All right, now let's go ahead and do the other easier one. Let's plug in 100 over here. And again, any number larger than 1 will do. So I get a positive number on top. I get a negative number on bottom. Again, that's negative, which is false. So you can be pretty sure you are going to shade in the middle. But on rationals especially, it always would be good to check. Okay, so I'm going to plug in 1/2. I'm going to have to actually do the number crunching here. 2 times 1/2, that gives me a 1, a positive 1, and really since we're comparing it to 0. This is another reason why I picked this one, because you really don't have to worry about what the number is, just if it's positive or negative. And 1 minus 1/2, that would be 1/2, but another positive number, that's going to give you a positive number. So we have a true statement. And so we shade in the middle. And so doing test points, it may seem tedious, but for rationals, it for sure is the way to go. The other ways that I have taught this and have been taught this are actually much more tedious than even this is. Okay, let's do another rational that's a little bit more complicated, meaning that we have more numbers to deal with. Okay, let's say we have x minus 2 over x minus 1, and that's less than 0. So it's already set up where it's compared to 0, which is nice. But what I don't have over here is a common denominator, so I need to do that. And I'm going to have to multiply x by x minus 1 to make that happen, top and bottom. Okay, so then I have x squared minus x minus 2 over x minus 1 less than 0. I'm going to take it just one step further and I'm going to factor it. X minus 2, x plus 1 over x minus 1. Now if you remember thinking about graphs, it's always best to have top and bottom in factored form. So my solutions to the equation would be x equals 2 and x equals negative 1. Now do you think these numbers are also solutions to the inequality? Okay, hopefully you said no or thought no, because this is just less than 0. So we're not looking for the or equal to part. So I'm going to have some open circles on these numbers. In fact, let's just go ahead and put that on the number line. Since we thought about it, we're going to write it. Okay, those numbers are just going to be boundaries. They're not actually solutions to this particular inequality. Now my vertical asymptote, okay, is at x equals 1. This is what we call a critical point, and this is going to go right here. This for sure is going to be an open circle because it can't be where this is true. 1 is where the graph drastically changes because it's a vertical asymptote. You don't even have to do anything else on these to know that it's open circle. Only the solutions you have to think about, is it or equal to or not. Okay, now let's do some test points. If we test over here, I'm going to test in a negative 100. And I'm going to actually look at this one. I'll show you why. Negative 100 squared is a large positive number. Doesn't matter what happens right here. Okay, on the bottom, okay, I would have negative 100 minus 1. That's negative 101, so I'd have a negative. So this is going to give me a negative number, which is then true because I'm looking for less than 0. So I am going to shade over here. And I've already kind of told you, you will get an every other, but with rationals, it's really hard to tell when and not. So you really need to do a test point in each section. Okay, here I have a 0. If I plug in 0, I end up getting a negative 2, okay, over a negative 1. Negative over negative is positive. I'm looking for where it's less than 0 though. So that's false. So don't shade right there. Okay, now we need to plug in a number between 1 and 2, like 1.5. All right, and I'm going to go ahead and put it as 1.5. And for this one only, I'm going to use this right here because 1.5 minus 2, that's going to give me, I kind of didn't leave myself a lot of room here. That's going to give me a negative number right here. But it's going to give me times a positive. So a negative times a positive over a positive. Okay, which is in turn going to give me a negative, which is false. Oh, I'm sorry, which is true because we're looking for less than 0. All right, and so we do shade right here. So you can be pretty confident you're not going to shade after the 2, but let's plug in a number just to check it anyway. If I plug in 100, back up to this one, I get a positive over a positive. Excuse me. That's not going to be less than 0. That's going to be false, so don't shade over there. So then my final answer is going to be negative infinity to negative 1, parenthesis, union, and then all the numbers between 1 and 2. If you have questions, please write them down, and you can either email me or bring them up in class tomorrow. Oh, I keep doing that. All right, next problem. So one other type of inequality that we haven't yet talked about, but it's really not that bad. And these are absolute value inequalities. Now, there's kind of two things you need to keep in mind. First, always isolate the absolute value. And if you want to write that in your notes, do that. Always, 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 always isolate the absolute value. We're not going to compare to 0 on these. We're actually just always going to have absolute value on one side and a number on the other side. Okay. So next step is, we have a couple of different methods. The method that I think you guys are most comfortable with is goal, and you may or may not have used this acronym, but you definitely use this idea. Now, what this stands for is, if you have an absolute value greater than a number, that's an or statement. If you have a less than, that's an and statement. So this is an and statement, and what this is actually saying is x minus 5 is less than 2, and x minus 5 is greater than, and then you switch it like we do with the equations, greater than negative 2, which is the same thing as negative 2 less than x minus 5 less than 2. Now, when you're really doing these problems, you're going to go straight from here to here, but I did want to kind of explain to you why this worked. Okay, think of it this way. If the distance between x minus 5 and 0 on the number line is less than 2, then that means this x minus 5, here's 0, it can only be 2 units away that direction, or it could be 2 units away over here. We're not talking about x, we're talking about x minus 5. It's somewhere in here. X is, we'll find in just a minute, but x minus 5 has to be trapped between negative 2 and 2. All right, because it's a distance that's less. It's a confined distance. All right, let's add 5 to everything to get our final answer. And we get 3 is less than x is less than 7. So we saw this at the very beginning of the lesson. It's all the numbers between 3 and 7. Now, if you don't like this, if this is confusing to you, you can definitely do test points. You can solve the equation, and if you had solved the equation, x minus 5 equals 2, the two answers would be x equals 3 and x equals 7. And then what you could have done is plotted 3 and 7 on a number line and then done test points. You would get the exact same answer is what I got. Okay? All right. Let's try another one of these. Let's say you have negative 2 times the absolute value of x minus 5 less than 2. All right, at first glance, this seems like another less than, but remember I said you got to always isolate the absolute value. So the first thing you got to do is divide by negative 2. And again, remember when you divide by a negative, that switches that inequality around. And so now you're thinking, okay, I have a greater than, so let's do the or statement. Actually, this is a special exception, and in this case, you do less work. Because what this is saying is the absolute value of something is greater than a negative number. Think about what that would mean. A distance of something, x minus 5 in this case, the distance between x minus 5 and 0 on the number line is greater than a negative number. That is, you got to think, it's not that it's not possible, it's that it's always going to happen. No matter where x is, when you subtract 5 and you take absolute value, whatever that distance is, even if it's 0, it's always going to be greater than a negative number. Okay, so how do we write always? We write it as all real numbers. Okay, and you don't want to do any other algebra to this because you'll get confused. Now, the no solution one would be like this. Let's say I had absolute value of x minus 5. This would be a different problem. Let's say this was less than negative, 20 or something. That would be a no solution for empty set. Okay, one last problem. Let's say we had absolute value of 3x plus 2 is greater than or equal to 4. So again, absolute value already isolated for you. If that hadn't happened, you would need to do that. Okay, this is, let me write the goal again. This is a greater than, so this means an or. So this means that 3x plus 2 is greater than or equal to 4, or 3x plus 2 is less than or equal to negative 4. Again, you switch up the number and switch up the inequality, but because we have an or, that's different. That's not overlapping. This is union. All right, so we're going to have to, there's no way to write this as one inequality. We solve these out separately. If I put this to you on a picture, here's 0. 4 units away would put you at 4 or at negative 4. And if I said the distance between 3x plus 2 and 0 was more than 4 units away, we're talking right here or right here. Okay? We're not talking in the middle. We're talking the outer edges. So you're going to have two different intervals and you're going to combine them with a union statement. And so just solve these out separately. These are just linear inequalities you would solve out separately. So I would have x greater than or equal to 2/3, or over here 3x less than or equal to negative 6, and x is less than or equal to negative 2. And so you would have to write the less than statement first, and it usually is the second one, but sometimes, you got to divide by a negative, and so just think it out from problem to problem. So we need to, if you want to draw a number line, you can. Negative 2. Less than or equal to negative 2 would be all of this. Here's 2/3. Greater than or equal to 2/3 would be all of this. So we have negative infinity to negative 2, bracket, union, bracket, 2/3. And I'm using brackets because of the or equal to part of my original inequality. And there you go. There's most of the types of inequalities, all the ones that you've learned before. There are other types, but these are the main ones. Please, please, please bring your questions to class.